What do you think this liquid is? It's crude oil, the basis for gasoline and kerosene. But it's not ordinary crude oil pumped out of an oil field. It's a synthetic fuel made from CO2. Let's see what happens when we ignite it. First, commercial kerosene. And then, the synthetic fuel. Synthetic fuel burns like kerosene. But, unlike kerosene, it produces no smoke, making it a very clean fuel. We're now conducting R&D on synthetic fuel production technologies at this integrated production bench plant. If we can make synthetic fuel from CO2, we can reduce carbon emissions, while also producing domestic energy that isn't dependent on fossil fuels. Synthetic fuel holds great potential. Synthetic fuel is made from CO2 and hydrogen. By refining a hydrocarbon compounds mixture that is similar to crude oil, we can extract gasoline, jet fuel, kerosene, and diesel. Synthetic fuels are attracting attention as a clean source of energy that can replace fossil fuels because their feedstock CO2 is captured from the atmosphere or produced from biomass. As you can see, fossil fuels account for over 80% of Japan's primary energy mix. And since Japan imports most of these fossil fuels, synthetic fuels are promising in terms of energy security. In September 2022, the Japanese government established the Public and Private Council toward the promotion of the introduction of synthetic fuel, e-fuel, to discuss the role of synthetic fuels. A big challenge in commercializing synthetic fuels is price, specifically the production cost. But we also have to overcome technical issues to identify its potential for CO2 reductions. AIST is a member of this council. We'll contribute to technological development and its commercialization in the near future. Synthetic fuel is produced by converting CO2 into syngas, and then converting that gas into fuel. The conversion to syngas is a process that changes CO2 into highly reactive carbon monoxide. This is the preliminary step to efficiently synthesize fuel. During the conversion to fuel, we produce synthetic fuel by using a catalyst to synthesize hydrocarbons from the carbon monoxide and hydrogen in the syngas. As a key part of AIST's synthetic fuel R&D, our production bench plant integrates solid oxide electrolysis cell (SOEC) co-electrolysis, a highly efficient electrolysis for the conversion process to produce syngas with Fischer-Tropsch FT synthesis for conversion into fuel. This bench plant is the first in Japan to implement an integrated production process for synthetic fuel through electrolysis. This plant can produce crude liquid synthetic fuel from feedstocks at a scale of 1 ton per year. To produce synthetic fuel more efficiently, we must develop catalysts as well as production processes. We are carrying out various research on these processes. Conversion to syngas. The typical method of producing syngas is to use a catalyst to carry out a reverse water-gas shift reaction to obtain a gaseous mixture of carbon monoxide and hydrogen from CO2 and hydrogen. However, AIST is developing an innovative process for producing syngas through electrolysis. Because CO2 is a chemically stable substance, the key to this process is how to convert it into a highly reactive syngas. Therefore, we are working on R&D to produce syngas from CO2 through electrolysis. One approach is CO2 electrolysis, which reduces CO2 to carbon monoxide using electricity. Another is co-electrolysis, which electrochemically reduces CO2 and water simultaneously. These innovative approaches differ from conventional methods, and if we can establish this production technology, we will be able to produce syngas more efficiently. Electrolysis involves the use of a solid device called an SOEC cell stack. Our goal is to achieve stable conversion to syngas while searching for more optimal methods of use and operation. Conversion to fuel. There are several methods of producing fuel from syngas, but AIST is focusing on FT synthesis. Since the synthetic fuel is produced from a mixture of various hydrocarbons, we only extract and use the desired components, such as gasoline or jet fuel. Developing new catalysts is one way that AIST is seeking to establish more efficient ways of synthesizing desired hydrocarbons. Catalysts are important in the process of converting syngas into fuel. This is an FT catalyst typically used for FT synthesis. It accelerates the FT reaction's progress. But if we only use an FT catalyst in the reaction, it yields a very wide range of hydrocarbons, from methane, a gas, to wax, a solid. This is where acid catalysts come in. Using an acid catalyst allows us to break down the unwanted wax components and increase the amount of liquid components we can obtain. We are currently developing a hybrid catalyst that combines an FT catalyst and an acid catalyst. The proportions of the components in a synthetic fuel can vary according to the combination of substances used as catalysts. For example, changing a catalyst can increase the ratio of gasoline. That means we can produce synthetic fuels tailored to a specific use. However, there are challenges. FT catalysts and acid catalysts have different optimal reaction conditions. So even if the FT reaction occurs, you may not be able to obtain enough of the expected effect from the acid catalyst. We're focused on developing acid catalysts that also function effectively under conditions for FT catalysts, with the goal of further improving our techniques for conversion into synthetic fuels. Scaling up the production process. AIST had been assessing catalysts and researching production processes for synthetic fuels in a lab or a small production facility. Now, we've scaled up to a bench plant. By scaling up to the bench level to produce the fuels for creating synthetic fuel at a rate of 1 ton per year, we are taking on new challenges and conducting the research to solve them.
The first thing we do to develop a performance catalyst is to search for catalysts in a small microreactor. At this time, the catalyst particles are usually very fine. We then gradually scale up for practical use, but that same catalyst may not perform as expected for large-scale production. For example, the product distribution may change. In other words, we have to develop catalysts that are suitable for large-scale production. Therefore, we developed a pellet-shaped catalyst that works well in the bench plant. This is another key part of the R&D that poses a very high hurdle.
There are only a few cases globally of a viable integrated production process for liquid synthetic fuel from electrochemical reactions and thermochemical catalytic reactions, and it's the first attempt in Japan. To commercialize the process, we have to scale it up by a factor of more than 1,000. We will gradually scale up the production equipment in collaboration with various partners, while also researching catalysts suitable for large-scale production. This is a big challenge, but we aim to establish more efficient and cost-effective technology for producing liquid synthetic fuels. Assessing synthetic fuels. Synthetic fuels have the advantage of utilizing existing infrastructure and engines, and are expected to be used in automobiles, aircraft, and other mobility applications in the future. Therefore, AIST is analyzing the properties of synthetic fuels and evaluating their combustion characteristics. We are also working to apply this knowledge to fuel synthesis technology. Here, we're using a single-cylinder test engine to assess how fuel properties affect engine performance. Observing the phenomenon is a complex, challenging task with a typical multi-cylinder engine. So we make an engineering assessment of an internal combustion engine with just one cylinder. We assess the state of fuel combustion based on the pressure inside the engine cylinder. We also assess the fuel's ignition and combustion traits, observe spraying, and analyze properties. The purpose is to improve fuel synthesis by providing feedback with data from how the fuel is used. In the future, we also want to propose new combustion methods and new engines that leverage the unique traits of synthetic fuels. AIST stands out for being able to research synthetic fuels from production to assessment. Our advantage is carrying out comprehensive research on synthetic fuels by forming teams of personnel from different fields. The assessment results will serve as feedback to synthesize fuels with even better properties. Energy is the foundation of the country. It is essential to our everyday lives. Because it is directly connected to our lives, introducing synthetic fuels takes time and involves many hurdles. AIST is working hard to clear each of these hurdles and deploy sustainable, efficient synthetic fuels. If we can develop feasible synthetic fuels, they will help Japan achieve carbon neutrality by 2050 and also bring about major changes in the global energy market. As leaders who will shape the future, we will keep taking on the challenge.